Welcome to confirmatory factor analysis. So we're finally getting to the point in our class where we can really talk about doing structural equation models. So today it's all about latent structures, so those latent variables. Before we get into confirmatory factor analysis, so it's important to give a brief reminder and refresher about exploratory factor analysis. So an exploratory factor analysis, if you remember, this is what we did way back in multivariate back in the spring semester. This is EFA is all about reducing data and the patterns of correlations. CFA is very similar in that same manner. It's exploratory, so with EFA, we have fewer preconceived notions or hypotheses, and we're just kind of exploring what the structure of the data looks like. In EFA, all of the factors or all of the indicators are loaded onto all of the factors, which is very different than in CFA. And remember, we talked about things like eigenvalues and scree plots and KMO and factor rotations. We're not going to be talking about any of those in CFA. So EFA compared to CFA. In EFA, it's exploratory, where CFA is confirmatory. So EFA is more about data-driven, kind of exploring the data, where CFA is more theory-driven. We're confirming our ideas. In EFA, all the indicators are loaded freely onto all factors. In CFA, they're only loaded on the factors that we tell it to load it onto. EFA answers the question, what's the structure of the data? What's the structure of the indicators? What's the structure of the factors? Where CFA is really, does my theory fit the data? My theory about these latent constructs and what measures them. EFA, there are no tests of significance, where CFA there are. We have our model fit indices and other tests of significance. So to begin, I want to talk about the different types of confirmatory factor analyses that you can do. And these are all based on just how many factors you have and how they're related to each other. So the most simple is the single factor. So this is just where you have one factor. As an example here, this is common factors as a latent construct, and we have goals, tasks, and bonds, fidelity, training, experience, consensus, cohesion, and satisfaction, all measures that indicate common factors. Alternatively, you could potentially have a multi-factor model where you have more than one factor. When we do this, we always correlate each of the factors when we're doing a CFA. We don't have any direct effects going between the latent factors. And then going out, so the latent factors are our exogenous variables, and our indicators are our endogenous variables. So goals and tasks and bonds are therapeutic alliance, fidelity, training, and experience is therapeutic effect, and consensus, cohesion, and satisfaction is dyadic adjustment. The third kind is hierarchical CFAs. So this is when we have a latent construct made up of latent constructs. So in this example here, we have our three latent constructs of therapeutic alliance and therapeutic efficacy and dyadic adjustment loading onto common factors. So we're not going to talk much about hierarchical latent factors because it's pretty rare in our work that we do that we actually do those kind of analyses, and that gets a little bit more in depth into latent CFAs that we're going to be getting into in this course. So we're going to be focusing mainly on single and multiple factor CFAs. So naming factors, what you call a factor is really important because it's going to be totally theoretical what you're calling that. So it's important that you do this very conscientiously and thoughtfully, and that it fits with the research and has a lot of validity to it. But there are three common fallacies in naming factors, and I want to talk about each of those. So the first of the three common fallacies in naming factors is the naming fallacy. This is where the fallacy is that just because you name it this doesn't really mean it really is this, or that we even understand what that is. Naming a factor requires critical thinking, strong understanding of literature and theory, and strong validity, that the indicators really are valid measures to indicate that construct. The second common fallacy is the reification fallacy. So the reification fallacy is all about the belief that a factor must correspond to something out in the real world, where in fact a lot of these latent constructs are really abstract concepts that may not actually exist per se in the real world. Latent factors are abstractions, and our factor may reflect something real, but it also may be nothing more than a statistical abstraction. So it's really important to understand that, like, just because we find it doesn't mean it exists in the real world. That's really up to making sure that our measures are strong, that it fits with our literature, that we're really clear about what this means and what this looks like in the real world. The third one is the jingle jangle fallacy. So this one is it sounds like a Christmas song, but the jingle jangle fallacy. The jingle fallacy is that the assumption that because different things are called the same thing, they might not be the same thing. So happiness and satisfaction may not be the same thing. And the jingle fallacy mainly occurs when we expect something to be the same, two things to be the same, but they have a very low intercorrelation. That really indicates they might be different things. The jangle fallacy is the opposite. So it's just something that just because we think things are different doesn't mean that they really are. We may think satisfaction and happiness are different things, when in fact they might be the same thing. So this is again the opposite, where things that we would expect to have a low correlation or a moderate correlation, in fact, have a very high correlation, indicating that they might be the same thing. So this is important when we're naming factors to consider and remember these three fallacies, and we don't fall into one of these three. So now we're going to talk about the rules for CFA. This is all about the specification and identification of CFA models and the rules that need to be followed. First, assumptions of CFA models. So CFA models assume that each indicator is a continuous variable represented as having two causes. So that continuous variable, or manifest variable, or indicator, has two causes. The first cause is that there is a single underlying factor, that latent factor, that the indicator is supposed to measure, like when we talked about dyadic adjustment above, or therapeutic alliance with goals, tasks, and bonds. That goals, tasks, and bonds measure that underlying factor of therapeutic alliance. The second possible cause is other unique sources of causation that aren't included in the factor and are represented by the error. So in a CFA, our indicator is expected to cause our underlying factor and error. Second thing here is that measurement errors are independent of each other and of the factors. So those errors are independent of other indicators and also independent of the underlying factor. And the third piece is that all associations between factors are unanalyzed. So we just give correlations between our factors. We don't actually look at doing direct effects between any of them. There is a rule also on how many indicators you need to have per factor. If you're doing a single factor CFA, you need to have at least 3 indicators on your latent variable. If you have a multiple factor CFA, so if there's 2 or more latent variables in there, you can have 2 indicators per factor, but even if you do, you might run into a lot of issues with estimation and errors and Haywood cases, all sorts of things. So even though you can have 2 indicators on a latent construct, it's much better to have at least 3, just like with a single indicator. And Kenny, who's a big statistician who did a lot of the groundwork in developing SEM, said that 2 might be fine, 3 is better, 4 is best, and anything more is gravy. So you want to have at least 3, 4 or 5 is much better. But 3 will still work. And it's very common to have 3. Another thing, indicators must be continuous. If you have any dichotomous or non-continuous, those interval ratio variables, you're going to have problems. And then, although you'll hear mixed things about this, it's best if all the indicators are on the same scale. That really helps a lot, although it's not necessary. So if you remember, one of the things that needs to happen in order for a CFA to be identified is that you have to set a scale for the latent variable. Well, now we're going to talk about that. There are 2 ways to create scales. You can have a unit loading identification, or ULI, or a unit variance identification, which is UVI. The difference between these is where they set the scale. And a ULI scaling, it fixes the factor loading of the first indicator to 1. Where in a unit variance identification, it fixes the variance of the factor to 1. So the ULI, the unit loading, unit is going to be, that's going to be your indicator. The unit loading identification, we're going to set that loading to 1. All other factors in there are estimated freely, and the variance of the factor is estimated freely. This is the default N+. So if you're going to do a CFA in N+, unless you add extra syntax, this is what it's going to do. It's going to do unit loading identification. Unit variance identification, again, fixes the variance of each factor to 1. Each of the factors' variance is set to 1. And then the syntax, so if you want to do this, because this is the other one is the default in M+, you actually need to tell it that you want to do UVI. So the way you do that is, as you see here in the example below, you would put asterisks next to the first indicator, so the first manifest variable for each of your factors, and then you just do your factor at 1, and that tells it to set the variance at 1. So that's if you want to do UVI. As you'll see here, see here a little later when we look at an example, there really isn't any difference between ULI and UVI in estimation, so it really doesn't matter which one you do. So unless you have a really good reason, just stick with the default. Make your life easy. Don't go to the other one, and just stick with ULI, and you'll know that you have a scale, and for the most part, there's not going to be any difference between ULI and UVI in the results that you're going to get. So here's an example of ULI, your unit loading identification. So as you can see here, the first manifest variable, so the first indicator on each of the latent constructs are set to 1. And you can see the little hook arrow, the little curved arrow on your latent constructs, those are there to indicate the variance, and the variance is set to estimate freely. So the variance estimates freely, as well as all of the indicators except for that first one. And then here's the unit variance identification, where all of the manifest variables are set to, so all of the indicators are set to freely estimate, but then the variance for each latent variable is set to 1. So again, ULI, UVI. I'm going to toggle back and forth between these so you can kind of see the difference in those. And again, ultimately, it's not going to make any difference really in how it will look. It's just two different ways to set the scale. ULI, this is the default in M+. So again, here's an example of UVI. This shows you the syntax and what it looks like, as well as what the variable looks like. This is one where there's just one, a single confirmatory factor analysis, but you can see they have the asterisk next to A1 to tell M+ to override your default. And then on the next line, they say arousal at 1. So the latent variable set the variance to equal 1. And that will do a UVI if you want to do that for any reason. So here I wanted to show you what I was talking about earlier about how there's really not any difference that you'll get in the results for UVI versus ULI. I'm going to kind of show you through these. So this is the estimate. This is the unstandardized results. On the UVI, you can see I have circled there that the variance for arousal is set to 1. And then the ULI, A1 is set to 1. And then arousal is 1594, so that's freely estimated. So you can see how the numbers work out. You can see that the numbers are quite different between those two, which you'll see in the unstandardized results. However, in the standardized, you really won't see much of a difference. So let's kind of compare those two when we look at those. And where those kind of come from and why they're not much different. One more piece between that. So when you do a UVI, you're setting that variance to 1, but where it's getting the scale for A1 is taking the variance of arousal, so the unrestricted variance of arousal, and then just taking the square root of that. And that's where you get that 39.925, that starting value for A1. So they're kind of similar to each other. It's just a matter of scaling. They're going to give you the same standardized solutions and fit indices. So there's not going to be any difference in which scaling you do. But it's important for you to understand the two pieces. So if for any reason you got a reviewer that just said, do ULI, you can respond and say, well, it's equivalent to UVI, and UVI is the default M+, so that's what we went with. Or you may say, fine, reviewer, we'll do ULI, and you have the syntax to know how to do that. So now interpreting results, how to interpret the results of a CFA. So first, make sure you follow the same process I talked about in the last lecture on output and interpreting results. So first, check your warnings and errors, check your model fit, double check your syntax and your paths, and then look at the factor loadings. When you're interpreting the pattern of coefficients, so in other words, your output for your indicators, Unstandardized factor loadings are interpreted just like any unstandardized regression. So keep in mind that the factor is our exogenous and the indicator is our endogenous. So the factor is our IV, the indicators are our DV. So in this, we would say as the factor goes up by 1 unit, the indicator changes by, insert the value for the estimate, units. You'll pretty much never report it in this way in journals. You're just going to quickly, kind of briefly report what the results of the model fit are. You may report some of the standardized factor loadings, but I wanted you to understand what those results mean when you look at the unstandardized results and what those are telling you. So if we go back to our example from before, for the unstandardized results, what we're saying is, if we look at the UVI, as the factor goes up by 1 unit, then A1 goes up by 39.925 units. Or on the other side, if we look at the ULI side, let's look at A2, as the factor goes up by 1, A2 goes up by 0. Now the standardized output, so that'll be your STDYX output. How you interpret those depends on whether you have simple or complex indicators. So in simple indicators, that's where the indicator depends on a single factor. They're equivalent to just Pearson's correlations. In complex indicators, where they depend on 2 or more factors, they're just like standardized regression coefficients. It'll also give you an R-squared output in your CFA. That R-squared is interpreted just like we did in multivariate statistics. Remember that the factors are IV and the indicators are DV in these in CFAs. So, if we had an R-squared for an indicator that's 0.78, you'd say the factor accounts for 78% of the observed variance of the indicator. This is helpful to know how much, because remember, we have 2 reasons for what that factor is causing. And if our factor loading is really small, or if our R-squared is really small, then that would mean that an error is a much higher proportion than we have really counted in the factor. So factor loading requirements for a CFA, when you're actually looking at the loadings to determine whether they are good loadings or not, you're going to look at the STDYX, so the standardized output there. And what we're really looking for is for the loadings to be 0.7 or higher. You'll see some authors say that each factor must be at 0.7 or higher, but really more broadly, the average of them should be at 0.7 or higher. So if you look at across your factors, you don't have to actually do the math and figure this out, but if you look at them, you should see that it should be that the average is 0.7 or higher. If you have a small sample size, you should really get rid of anything below 0.6. And also pay attention to negative factor loadings, because if you have any factor loadings that are negative, first of all, that's going to make your model fit be atrocious. But what that means is you forgot to reverse code something. So you need to go back to your data and recode that and then resave your file for M+, and then use that. And before you remove an item, so if you have a low item that you're considering removing, really think through that, because there are some types of things you could do around model fit to increase that without losing that variable, unless it's really low. But before you remove it, just really think about what that means for your latent factor if you're losing that item, because you included that item there for a reason. You thought that it had an important dimension or aspect of the latent construct that was important to you. So before you remove it, think about, what does this mean about the latent factor if I remove that manifest variable, if I remove that information? Does that change the latent factor in some way, or is it missing some important piece of that latent factor? So now to close out, we're going to look at an example of CFA. So the example I'm going to show you is actually from the 2nd edition of Klein's book, which you're not using this semester, but this will give you a good example. So in this example, which is a modification from an article from Williams, they are looking at affect and cognitive arousal in children. So the affect is feelings and cognitive is thinking. So how do we get kids like emotionally and thoughtfully engaged? And they had 5 variables for each of them. So the hypothesized model looked like this, where you had affect arousal, and they used A1 through 5 just to kind of indicate those variables, and then cognitive arousal, so you have the C1 through 5. And this is the hypothesized model. When they're inputting the data in, this is the correlations table, so you can kind of see what the correlations look like between each of the factors with each other, and you can see that they're largely really strong, which is what we want to see with a factor analysis. We want to see good correlations because they're going to be all measuring, some latent construct. So one thing that's really important, even if you hypothesize that there are 2 or 3 factors in a model, it's important to first test it as a single factor because remember, we want to be as parsimonious as possible. So in this example, let's first look at testing the single factor. Let's look and see if perhaps just arousal is the best way to look at it. So here's the syntax for this. So we're going to use the by statement to indicate it's a factor, and then not having any extra syntax around A1 or arousal. We're just going to be doing ULI. That's the default in here. You can see in the output we have stamp stats, so that'd be your sample statistics, mod indices, so you get modification indices, residual, and standardized. However, I'd recommend you do STDYX instead of standardized in there. And again, mod indices, you do that 3.84 would be helpful to do as well. So here's a slide on how to interpret the unstandardized factor loadings. This is exactly what we were talking about before around how you interpret them, just as you do with unstandardized regression weights where your estimate is your beta in that. And that you can see we have the ULI because our A1 is set to 1 and arousal variance is not set to 1, it's set to estimate freely. And here's more on the unstandardized. This slide shows exactly what we were talking about before about how you actually interpret the factor loadings in that unstandardized way. So 1 unit change in the factor leads to 1 unit change in A1 or 0.979 in A2. Keep in mind that these factor loadings will kind of help you see which ones are stronger than the others. Like you can see A5 is 1.07. However, keep in mind that when you're comparing it to A1 or comparing these, keep in mind that it's all in relation to A1 being set to 1. So you can get into fallacies if you try to go too far with that. So here are the standardized factor loadings. So remember with the simple one, these are equivalent to correlations. Where like A1 being 0.886 is just a correlation between that and the factor. So those are just simple correlations. Then we have our R squared. So like A1, the factor accounts for 78% of the variance in A1. And also you can kind of see through these standardized factor loadings, they're all well above 0.7 or average is way above 0.7. So I'm pretty happy with these factor loadings. So let's take a look at the model fit here in a second. This is a diagram that shows you what those factor loadings look like. So we have our unstandardized results here on this, and then on the next slide we have our standardized results. So you can see when we go to the standardized results, the variance is 1 for arousal. We haven't switched to the other one, to UVI. We're still on ULI. So the unstandardized, you can see where the ULI, we're using ULI because it's set to 1, but the standardized, we now have the results in here. So you can see they're all above 0.7. This is looking very nice. I'd be very happy with this, but what does the model fit look like? So here's the model fit. So take a moment and look at this and tell me, and ask yourself, does this look like good model fit? So if you look at this, chi-squared is not significant, so that's not great, but again, large sample size, it often will be. The CFI and the TLA are both below 0.9. They're pretty bad. The RMCA is 0.223. That's atrocious. And our SRMR is 0.083, so it's not terrible. But our RMCA and our CFI and our TLA are not good. So I'm not very happy with this. So now let's look at making it into a two-factor CFA, like was originally hypothesized, where we have affect with our A1 through 5 and our cognitive by C1 through C5. There's a new output in here, Tech4. This will give you the covariance and correlation matrix among the factors. So if you want that, that's how you do that. There's not often where you do need that, but if you want it, that's how you get it. So since we already showed you the step-by-step in the one factor, we're just going to skip straight to the standardized solutions for this two-factor approach. You'll see in here we have a value for the correlation between the two factors, 0.81, so their correlation is 0.81 between affect and cognitive arousal. And then we can see that our factor loadings for the standardized for these, 0.90 and higher for affective and above 0.8 for cognitive, so this is even better factor loadings this way. Let's take a look at the model fit. So you tell me, does this model fit look good to you or does it look better? If you look at it, you'll see our chi-squared is still 0, is still significant. So the value is much smaller, but it's still significant. Our CFI and TLI, however, are both above 0.97, so they look great. Our RMCA went from 0.2 to 0.086, so that's much better. That's better in the range of what we want to see it. And our SRMR is 0.02, so that's good too. This is much better model fit. So when you're doing model comparisons, I talked about this a lot in the last lecture, but if we're doing models that are hierarchical, so that one is nested within the other, like in this case we have a single and our double factor, that chi-square difference test can tell us if they are significantly different from each other. So we do that by just doing that, taking the difference, just like I talked about in the last one. So our single factor model, we look at our chi-square, 411 minus 88 gives us 322. And then we take our degrees of freedom. There's one difference, so 322 with 1 degree for instance, p is less than 0.05. So our chi-squared, if it is significant, it means the models are significantly different from each other. If you want to know if that's significantly better or worse, you have to look at the model fit between the two and understand the context. In this context, our model fit got better, and so they're significantly different, so it got significantly better, which means our two-factor is a much better fit to the data than our single factor, so we should use our two-factor rather than our single-factor model. Now, the final step I want to talk about is respecification. So we kind of did that there, where we kind of respecified by going from a 1 to a 2-factor, but I want to talk a little bit about this in more detail. So when you're testing CFA models, even when theory is very specific about the number of factors, like in that example where there are 2, you should still determine whether 1 factor or fewer factors is a better fit. So start with 1, then move out, and see if 2 factors is a significantly better fit than a single factor. And lastly, as is often the case in SEM, your initial model may not fit the data very well. So respecifying is very important. When you're respecifying the model, consider the number of factors. You may need more than 1 factor. Consider the relationship of the factors to the indicators. So those factor loadings. There have been times where I've seen that a factor loading is a better fit on a different factor than the factor I had it loaded on. And look at the pattern of measurement, or look at the patterns of error correlations, and look at the pattern of correlations between the variables. Given so many potential variations, respecification, it's very important that that's guided as much as possible by substantive considerations, so things that will make a big difference. In our next module, we're going to get to full structural models. So models that have latent and manifest variables, and we're going to talk about how to run them, how to interpret them, how to write them up in scholarly journals, how to do tables, all of that stuff. That's what we're going to cover in our next module.